The P-51 Mustang rolled down the runway at Wright Field, Ohio, its Merlin engine purring with mechanical precision. Captain Chuck Yeager adjusted his grip on the stick, feeling the familiar weight of 489 gallons of fuel distributed across internal tanks and wing drop tanks. According to every manual, every specification sheet, every engineering calculation, this fuel load would carry him 1,650 miles in combat configuration. But as Yeager lifted off into the gray December sky of 1944, he knew those numbers were about to become completely irrelevant. What happened next would violate every principle of fighter aircraft operation the Army Air Forces had ever taught. It would horrify engine manufacturers, terrify commanding officers, and ultimately revolutionize long-range fighter tactics across every theater of World War II. Because Chuck Yeager was about to discover that the most efficient way to fly a fighter wasn't efficient at all, it was controlled destruction. The mission brief had been straightforward enough. Test the P-51's maximum range capabilities under combat conditions, push the aircraft to its absolute limits, and document fuel consumption rates across various flight profiles. Standard procedure called for maintaining optimal cruise settings throughout the flight. Lean fuel mixture, moderate RPM, conservative throttle management, the kind of by-the-book flying that kept engines running smoothly and pilots alive. But Yeager had noticed something during previous flights that the engineers apparently missed, something that contradicted everything they thought they knew about reciprocating engines and fuel efficiency. When he pushed the Merlin engine past its recommended limits, past the red lines marked on every gauge, something extraordinary happened. The engine didn't just survive the abuse, it actually became more efficient. The discovery had started 3 weeks earlier during a routine training flight over the Nevada desert. Yeager had been testing the P-51's performance at various altitudes when German fighters appeared on the horizon, real ones, a formation of Messerschmitt Bf-109s that had somehow penetrated American airspace, probably long-range reconnaissance aircraft probing coastal defenses. Standard intercept procedure called for climbing to altitude advantage while maintaining fuel reserves for extended combat. But these Germans were already at 28,000 feet and accelerating toward the Pacific coast. If Yeager followed doctrine, they'd escape before he could engage. So he made a decision that should have destroyed his engine and ended his career. He firewalled the throttle, pushed the propeller control to maximum RPM, and shoved the fuel mixture to full rich. Every gauge in the cockpit immediately moved into the red zone. Engine temperature climbed toward dangerous levels. Fuel flow increased to rates that should have emptied his tanks in minutes. The Merlin engine began producing power levels that Rolls-Royce engineers insisted would cause catastrophic failure. Instead, the P-51 climbed like a homesick angel. Yeager caught the German formation at 32,000 feet, engaged them in a brief but decisive dogfight, and shot down 2 Bf-10-9s before the survivors fled toward Mexico. When he landed back at Wright Field, his fuel gauges showed something impossible. He'd flown for 2 hours at maximum power settings and consumed less fuel than predicted for normal cruise flight. The ground crew couldn't believe the readings. Neither could the engineering officers who examined the flight data. According to every textbook, every formula, every principle of internal combustion engine operation, running an engine at maximum power should increase fuel consumption exponentially. But Yeager's data showed the opposite. The harder he pushed the Merlin, the more miles he got per gallon. The engineers demanded a repeat test. Yeager obliged, this time with observers monitoring every instrument from the ground via radio telemetry. The results were identical. Maximum power settings produced maximum fuel efficiency. It seemed to violate the laws of physics. Dr. James Morrison, the lead propulsion engineer at Wright Field, spent 3 sleepless nights analyzing the data. His calculations showed that Yeager's technique should have been impossible, but the numbers didn't lie. Somehow, running the engine at redline conditions was extracting more energy from each gallon of aviation fuel than conservative cruise settings. The breakthrough came when Morrison realized they'd been thinking about the problem backwards. Everyone assumed that gentle engine operation meant efficient engine operation, but the Merlin wasn't designed for gentle operation. It was designed for war, and in war, efficiency sometimes meant accepting controlled destruction in exchange for maximum performance. The key was understanding what happened inside the engine when Yeager pushed it beyond recommended limits. At maximum power settings, the combustion chambers reached temperatures and pressures that created more complete fuel burn. Instead of wasting unburned hydrocarbons through the exhaust, the engine was extracting every possible BTU of energy from the fuel mixture. But this efficiency came at a devastating cost. The engine components were operating under stresses that would normally cause failure within hours. Pistons, valves, bearings, all experiencing loads far beyond their design specifications. The technique would work, but only for a limited time before the engine destroyed itself. Morrison brought his findings to Colonel James Doolittle, who immediately grasped the tactical implications. If American fighters could extend their range by 50%, even at the cost of engine life, it would revolutionize bomber escort missions over Europe and the Pacific. The ability to accompany B-17 and B-24s deeper into enemy territory could turn the tide of the strategic bombing campaign. But first, they needed to prove the technique worked consistently across different aircraft and different pilots. Yeager's results might have been a fluke, an anomaly caused by unique atmospheric conditions or measurement errors. The only way to validate the discovery was through systematic testing under controlled conditions. On December 15, 1944, Wright Field assembled a squadron of test pilots to evaluate what they were already calling the Yeager Technique. 6 P-51 Mustangs, each equipped with identical fuel loads and instrumentation. 6 pilots with varying experience levels, from recent flight school graduates to combat veterans with hundreds of hours in type. The test protocol was elegantly simple. 3 aircraft would fly a prescribed route using standard cruise procedures. 3 would fly the identical route using Yeager's maximum power technique. All 6 would maintain radio contact throughout the flight, reporting fuel consumption and engine parameters every 15 minutes. Captain Bob Hoover, who would later become one of aviation's most celebrated test pilots, flew as Yeager's wingman during the trials. Years later, he would describe the experience as simultaneously terrifying and exhilarating. The engine noise alone was enough to convince most pilots they were about to experience catastrophic failure. The Merlin roared at maximum RPM, every mechanical component stressed to its absolute limit. But the fuel flow data was undeniable. The aircraft using Yeager's technique consistently showed lower fuel consumption rates, despite producing significantly more power. The physics seemed impossible, but the results were reproducible across different pilots, different aircraft, and different atmospheric conditions. Dr. Morrison finally understood why the technique worked when he examined high-speed photography of the combustion process. At maximum power settings, the fuel-air mixture burned more completely due to higher chamber pressures and temperatures. The engine was essentially achieving a more perfect chemical reaction, converting more of the fuel's potential energy into mechanical work. The trade-off was brutal. Engines operated using the Yeager technique showed accelerated wear patterns that would reduce their operational life by 60 to 70%. But in wartime, that calculation made perfect sense. Better to have an engine last 200 hours and complete the mission than last 500 hours and fail to reach the target. Word of the technique spread quickly through the Army Air Forces, but with strict classifications attached. The knowledge was too valuable to risk German intelligence discovering the method. American pilots began receiving classified briefings on extended-range procedures, though most never learned the specific techniques involved. But implementation would prove far more challenging than discovery. Because the Yeager technique wasn't just about pushing throttles forward and accepting engine damage. It required precise understanding of engine limitations, fuel management, and thermal dynamics. One mistake could turn controlled destruction into catastrophic failure at the worst possible moment. The training program began at Wright Field in January 1945, where pilots learned that the Yeager technique was actually 3 distinct procedures working in deadly harmony. Each one violated established doctrine, and together they created a fuel efficiency paradox that would redefine fighter operations for the remainder of the war. The first procedure, which pilots dubbed thermal shock initiation, required bringing the engine to maximum operating temperature as quickly as possible. Instead of the gradual warm-up prescribed in every flight manual, pilots would advance throttles to military power within 60 seconds of engine start. This sent coolant temperatures spiking toward the red line, while oil pressure fluctuated wildly. Lieutenant Robert Johnson, fresh from P-51 training at Luke Field, nearly refused to attempt the procedure during his first briefing. Everything about it contradicted the methodical engine management he'd spent months learning. But instructor pilots explained that the Merlin's combustion chambers needed extreme heat to achieve the molecular changes that made the technique possible. The second procedure was even more counterintuitive. Once airborne, pilots would cycle the engine through what engineers called controlled detonation phases. This meant deliberately inducing conditions that would normally cause engine knock, the destructive phenomenon that could destroy pistons in seconds. But by carefully managing fuel mixture and ignition timing, pilots could create controlled micro-explosions that increased thermal efficiency. The technique required pilots to listen to their engines with unprecedented attention. The sound of controlled detonation was distinctly different from dangerous engine knock. Controlled detonation produced a sharp, rhythmic hammering that experienced pilots learned to recognize. Dangerous knock created an irregular, chaotic noise that meant immediate power reduction or engine failure. Captain Frank Everest, who would later set multiple speed records in experimental aircraft, described learning the technique as educational torture. Hours spent in the cockpit with engine temperatures dancing along failure points, while instructors coached him through audio recognition of different combustion patterns. One mistake could destroy a $50,000 engine and potentially kill the pilot. The third procedure was the most dangerous because it required pilots to operate engines in conditions that guaranteed eventual failure. Maximum continuous power meant running at settings that would destroy the engine within a predetermined time frame. Pilots had to calculate exactly how long they could maintain these settings before mechanical failure became inevitable. The mathematics were brutal but precise. A Merlin engine running at maximum continuous power using the Yeager technique would consume its operational life at approximately 3 times normal rate. But during that accelerated consumption, it would produce fuel efficiency gains of 40 to 60%. The trade-off meant sacrificing long-term engine life for immediate tactical advantage. Training pilots to manage this calculation required teaching them to think like engineers rather than aviators. They needed to understand bearing temperatures, compression ratios, and metallurgical stress limits. Information that had previously been the exclusive domain of ground maintenance crews now became essential pilot knowledge. Master Sergeant William Murphy, who maintained the test aircraft at Wright Field, watched pilots struggle with concepts that mechanics learned through years of hands-on experience. These combat veterans could execute complex aerobatic maneuvers under enemy fire, but understanding why aluminum pistons behave differently at various temperatures challenged them in entirely new ways. The breakthrough in training methodology came when instructors began using automotive analogies. Most pilots understood that racing car engines produce more power but required more frequent rebuilding. The Yeager technique was simply applying racing engine principles to military aviation. Maximum performance extracted through controlled destruction, but implementation in combat theaters revealed complications that laboratory testing had never anticipated. European weather patterns created atmospheric conditions that affected engine performance unpredictably. What worked perfectly at Wright Field consistent altitude and temperature might fail catastrophically over the North Sea in winter storm conditions. Colonel Francis Gabreski, commanding the 56th Fighter Group in England, received the first operational briefings on the Yeager technique in February 1945. His initial reaction was skepticism bordering on disbelief. He'd seen too many pilots killed by engine failures to willingly accept procedures that deliberately stressed power plants beyond design limits. But the strategic situation demanded desperate measures. German jet fighters were appearing in increasing numbers over the Reich. The Messerschmitt Me 262 could outrun any piston engine fighter in level flight. American P-51s needed every possible advantage to engage the jets effectively, including extended range that would allow pursuit deeper into German airspace. Gabreski authorized limited trials with volunteer pilots from his most experienced squadrons. The men chosen were combat veterans with hundreds of hours in P-51s and proven ability to make life-or-death decisions under extreme pressure. If anyone could master the technique safely, it would be these pilots. The first operational test occurred during a bomber escort mission to Berlin on March 8, 1945. 4 P-51s using conventional fuel management accompanied the bomber stream using standard procedures. 4 others employed the Yeager technique from takeoff to landing. All 8 aircraft carried identical fuel loads and flew identical routes. The results exceeded even the most optimistic projections from Wright Field testing. The aircraft using the Yeager technique not only completed the mission with fuel reserves remaining, they were able to pursue German fighters an additional 60 miles beyond the point where conventional aircraft had to turn back due to fuel limitations. But success came at the predicted cost. Post-flight engine inspections revealed accelerated wear patterns that would require complete engine replacement within 50 flight hours. The technique worked exactly as advertised, providing tactical advantages through controlled mechanical sacrifice. Word spread quickly through 8th Air Force fighter groups, though officially the technique remained classified above top secret. Pilots began receiving coded briefings on extended range procedures without learning the specific methods involved. Only squadron commanders and flight leaders received complete technical training. The secrecy created dangerous situations when pilots attempted to reverse engineer the technique from incomplete information. Several aircraft were lost due to engine failures caused by improper implementation of procedures they only partially understood. The line between controlled destruction and catastrophic failure was measured in precise temperature and pressure tolerances. By April 1945, the Yeager technique had been adapted for use in P-47 Thunderbolts and P-38 Lightnings, each requiring aircraft-specific modifications to accommodate different engine characteristics. The Pratt & Whitney R2800 radial engine responded differently to thermal shock than the liquid-cooled Merlin. Allison engines in the P-38 required entirely different detonation management procedures, but the fundamental principle remained constant across all aircraft types: maximum efficiency through controlled destruction, trading engine longevity for tactical advantage. It was a philosophy that perfectly captured the desperate desperate mathematics of total war where victory justified almost any sacrifice. The adaptation process revealed just how much the technique depended on understanding each engine's unique personality. Lieutenant Colonel David Schilling, commanding the 56th Fighter Group's conversion to P-47 Thunderbolts, discovered that the massive R2800 radial engine required completely different thermal management than the sleek Merlin. Where the P-51's liquid-cooled system responded predictably to temperature changes, the air-cooled Thunderbolt created hot spots that could destroy cylinders without warning. Sergeant First Class Tony Ricci, a maintenance chief with 15 years of radial engine experience, became an unlikely instructor in the technique's mechanical principles. He'd spent his career teaching pilots to baby their engines, to treat every component with mechanical sympathy. Now he found himself explaining why deliberate abuse could actually improve performance. The R2800's 18 cylinders created thermal dynamics that baffled even experienced mechanics. Unlike the Merlin's uniform cooling system, each cylinder in the radial arrangement experienced different temperature conditions depending on its position relative to the propeller wash. Implementing the Yeager technique required pilots to understand how heat distribution affected individual cylinder performance. Ricci developed a training program using cutaway engines that showed pilots exactly what happened inside their power plants during extreme operating conditions. Pistons expanding beyond normal tolerances, valves opening at temperatures that would soften their metal composition, bearing surfaces operating with oil viscosity reduced to nearly water-thin consistency. The visual education was both fascinating and terrifying. Pilots could see mechanical components operating in conditions that should have caused immediate failure, but they could also understand why those extreme conditions produced more complete fuel combustion and higher thermal efficiency. Captain Robert Johnson, now qualified in both P-51 and P-47 variants of the technique, described the difference as night and day. The Mustang's technique felt surgical, precise, requiring constant attention to coolant temperatures and mixture settings. The Thunderbolt's version was more like controlled violence, managing 18 individual explosions occurring thousands of times per minute. But the P-38 Lightning presented the most complex challenge because its twin Allison engines required perfect synchronization to avoid catastrophic asymmetric thrust conditions. If one engine failed while operating at maximum power settings, the resulting yaw forces could tear the aircraft apart before the pilot could compensate. Major Richard Bong, America's leading ace with 40 confirmed victories, volunteered to test the P-38 adaptation despite concerns from his commanding officers. His combat experience in the Pacific Theater had taught him that range limitations were often more dangerous than enemy fighters. Japanese bases scattered across thousands of miles of ocean meant that fuel exhaustion killed more American pilots than bullets. The twin-engine technique required pilots to monitor 4 separate temperature gauges, 2 oil pressure indicators, and dual fuel flow meters simultaneously while maintaining formation position and watching for enemy aircraft. The cognitive workload was staggering, pushing human attention capabilities to their absolute limits. Bong's first test flight nearly ended in disaster when the port engine began showing signs of bearing failure during the controlled detonation phase. Standard procedure would have required immediate power reduction and return to base, but the technique demanded maintaining maximum settings until either mission completion or catastrophic failure, whichever came first. The gamble paid off. The bearing held together just long enough to complete the test profile, demonstrating that the P-38 could achieve range extensions comparable to single-engine fighters. But post-flight inspection revealed damage that would have progressed to complete engine failure within another 30 minutes of operation. News of the technique's success reached the Pacific Theater through classified channels in April 1945, just as American forces were preparing for Operation Downfall, the planned invasion of Japan. The strategic implications were enormous. P-51s operating from Iwo Jima could now escort B-29's bombers all the way to targets in northern Honshu, previously beyond fighter range. General Curtis LeMay, commanding the 21st Bomber Command, immediately grasped the tactical revolution represented by the Yeager technique. His B-29s had been conducting unescorted missions over Japan since March, accepting heavy losses to achieve strategic objectives. Fighter escort using extended range procedures could dramatically reduce bomber casualties while maintaining offensive pressure. But implementing the technique in the Pacific required modifications for tropical operating conditions that Wright Field's temperate climate testing had never encountered. High humidity levels affected engine cooling efficiency unpredictably. Corrosive salt air accelerated bearing wear beyond even the technique's normal degradation rates. Fuel quality variations between different supply bases created combustion inconsistencies that could trigger catastrophic detonation. Colonel Neil Kirby, who had pioneered long-range fighter tactics in the Southwest Pacific before his death death in combat, had left behind detailed notes on fuel management that became crucial for tropical adaptation. His observations about atmospheric density effects on engine performance helped engineers understand why the technique worked differently at different altitudes and temperatures. The adaptation process revealed that successful implementation required far more than simply pushing throttles forward and accepting engine damage. Pilots needed to become amateur meteorologists, understanding how atmospheric pressure changes affected combustion chamber dynamics. They needed mechanical intuition to recognize subtle audio cues that indicated impending component failure. Most importantly, they needed the psychological conditioning to operate expensive, complex machinery in ways that violated every instinct about mechanical preservation. Training programs expanded beyond technical instruction to include what psychologists would later recognize as stress inoculation therapy. Pilots practiced making critical decisions while listening to engines operate at the edge of destruction. They learned to distinguish between normal mechanical stress noises and sounds that indicated immediate emergency conditions. The program produced a new breed of pilot, part aviator and part engineer, capable of extracting maximum performance from machines through intimate understanding of their mechanical limitations. These men could coax an extra 100 miles from fuel tanks by precisely managing the controlled destruction of irreplaceable power plants. As spring turned to summer in 1945, the Yeager technique had evolved from Chuck Yeager's accidental discovery to a systematic methodology employed by fighter squadrons across both European and Pacific theaters. Pilots were achieving range extensions that fundamentally changed the strategic equation of aerial warfare, turning previously impossible missions into routine operations. But the technique's greatest test was yet to come. As Allied forces prepared for the final assault on Japan, American fighters would need to demonstrate that controlled destruction could produce not just extended range, but decisive tactical advantage against an enemy fighting with the desperation of the doomed. The mathematics of war were about to demand the ultimate validation of Yeager's revolutionary discovery. The summer of 1945 would prove whether trading engine life for tactical advantage could help end the most destructive conflict in human history. In cockpits across the Pacific, pilots prepared to push their aircraft beyond every design limitation, knowing that mechanical failure might mean death, but that success could mean victory. When Japan surrendered on August 15, 1945, Chuck Yeager's accidental discovery had quietly revolutionized fighter aviation across two theaters of war. The technique that began with one pilot's desperate intercept over Nevada had extended American fighter range by thousands of collective miles, escorted countless bombers to targets previously beyond reach, and turned mechanical destruction into tactical advantage. But the real victory wasn't measured in miles per gallon or engine replacement schedules. It was found in the fundamental shift in thinking that separated average pilots from exceptional ones: the willingness to challenge established doctrine when circumstances demanded innovation, the courage to accept calculated risks when conventional wisdom offered only certain failure. Yeager's technique proved that sometimes the most efficient solution isn't efficient at all. Sometimes survival demands controlled destruction, and sometimes the difference between victory and defeat comes down to one pilot's willingness to push beyond every red line, every safety margin, every limitation that lesser men accept as absolute. The next time conventional wisdom tells you something is impossible, remember Chuck Yeager climbing toward those German fighters, firewalling his throttles, and discovering that the most dangerous choice was actually the safest one. Innovation doesn't come from following the manual, it comes from having the courage to rewrite it.